likely to do it along a seam. But there's one glaring exception.
Hawaii is dead in the middle of a plate. Plate tectonics doesn't explain a place like Hawaii. So that's sort of a problem. So what people call on is this theory called Mantle Plume theory. And the idea, right, is so thermal convection is hot stuff is less dense, cold stuff is more dense, cold stuff goes down, hot stuff comes up. So you imagine convection as the boiling of water on your stovetop, right? Right. In the Earth, that convection is happening in solid rock. Yeah, so we're talking about motion of solid rock, right? Because at those time scales and at those length scales, the ground, the solid rock that you feel is as viscous as the maple syrup that you're pouring.
That's amazing. So this is rock moving through rock.
Yeah.
Wow.
So if you scale things the way that we think that they scale, it looks like a lava lamp, right? You have some hot stuff rising, and it starts with a big blob, and then there's this long, skinny tail behind it. The same physics happens in like nuclear bombs, right? You know, the mushroom cloud is the same idea, right? There's that big buoyant plume, and then the tail, the skinny tail behind. So the idea is that Hawaii and the Hawaiian Islands and these other hotspot volcanoes are that tail.
Hold on. So, this mantle plume theory says that an unusual hotspot like Hawaii is just the tail end of that blob shape of solid rock rising through solid rock. That's it.
So then you might ask, well, where's the bubble? Where's the bubble? People have argued is that those bubbles are these things called flood basalts. This is good, I promise. This huge bubble just explodes onto the surface, and so most of Siberia is covered in lava flows, and most of India is covered in lava flows. Individual lava flows that are hundreds and hundreds of feet tall that cover an entire country.
Wow.
And
so that was, I mean,
is covered in lava flows, and most of India is covered in lava flows. Individual lava flows that are hundreds and hundreds of feet tall that cover an entire country.
Wow.
And
so that was, I mean,
that's
like,
the thought is that was the bubble.
Bubble exploding?
Yeah,
or?
that's that bubble exploding into the surface. This is the tail and the head.
Yeah. And then as the head gets higher and higher, the pressure is released. And that means that the solid rock is going to start turning from a solid into a liquid.
Yeah, and so that's what we call magma. And
so
the reason
have
it's
we
super
ever seen anything like that happen?
Never.
Would it be an incredibly violent event?
Well, this gets good. There have been many extinctions in Earth history, and many of them correspond with when we think these bubbles explode to the surface. So the most recent one was 40 million years ago, and it was tiny, like a thousandth of the size of some of these. Yeah. But the largest extinction in Earth history, the Permo-Triassic, happens during the largest flood basalt.
So yeah, let's hope that doesn't happen anytime soon. Okay, so recap. The Hawaiian Islands are forming on a hotspot that's the result of one of these mantle plumes popping up through the crust like a hot pimple. You're welcome. And this might tell us something about the geology on the planet Mars.
We think that plate tectonics is not happening on Mars, but we think that probably mantle plumes are, and that's why we have these giant volcanoes like Olympus Mons. Okay. And part of why Olympus Mons is so big is because there's not plate tectonics. Right? So stuff's sort of piling up in the same place. But in Hawaii, because the plate is moving, you get snapshots. It's exactly like how your video camera works, right? Is you're taking a series of stills, and you can see the progression through time. And so what we see in the Hawaiian chain is a series of stills of the island through time. So when you go to the big island, that's it being born. And then you can trace that chain of islands to here, which is 5 million years. And you can trace it all the way to Japan. All the way up to Siberia. Really? Yeah, you go.
That is the line of the motion of plates over that one.
Yes.
Do me a favor, go to Google Maps or Google Earth and pull up the Hawaiian Islands. Maybe after you finish watching this video. Turn on satellite view and you'll see a line of old mountains traced by the same hotspot all the way up to Siberia. It's incredible, and you'll notice the line is crooked, which means that at some point the plate just changed direction, which is weird, but crazy that you can tell something like this about history from looking at the ocean floor.
So you can take the distance between the Hawaiian Islands. We actually know the ages, and you can calculate a velocity. And those are the same velocities that we measure with GPSs now. Actually see that.
That's so cool.
Yeah, it's really cool.
So there's a lot of stuff we're still learning about the Hawaiian Islands.
You can calculate a velocity. And those are the same velocities that we measure with GPSs now. Actually see that.
That's so cool.
Yeah, it's really cool.
So there's a lot of stuff we're still learning about the Hawaiian Islands. Thanks to Noah for trying to quench. This episode is brought to you by CuriosityStream. Electromagnets, and that kind of stole the show. And whoever you were in the comments that questioned my choice of physics classes because I had never seen liquid oxygen and I get excited by freshman level physics demonstrations, who killed your joy? Anyway, the real hero of my easily amused physics-loving heart was the tiny spark that forms when you turn off the electricity to the electromagnets. Because Josh, the gentleman from the MIT Technical Services group showing me these demos, promised a demo with an even bigger spark.
We actually have one that will do a huge back EMF when you lift it.
Oh.
We could just wheel that one out.
He did not disappoint. Side note, pyrotechnics is sometimes a side effect of demos meant for this pesky thing called learning. So we'll get that out of the way real quick. This demo had 2 giant coils of wire with another wire laid over the top. When you flip the switch to allow electricity to run through the coils, the wire on top jumps off. Meh, it's kind of wondrous. It shows induction, which is a really counterintuitive and awesome phenomenon in physics, so that's cool. Induction happens when a changing electrical current induces a current in a nearby wire. Induction is like the bad influence kid of physics. It induces you to have a current too, but there can only be one bad kid, so it pushes you apart. That made no sense. It's really just because of the magnetic fields produced by the currents that push them apart, but learning. Now when we turn off the current, things get real saucy. Okay, that jumped off and then, oh my gosh! That spark is from turning off the current. This demo is the universe telling you it is not happy with change. Sesame Street must be in my life forever! But really, inductors don't like it when you turn off their current. What? Oh right, what's an inductor? Those giant coils of wire, or this thing on a circuit diagram, or these things if you do electronics. But basically, an inductor is just a slinky connected to electricity, and it doesn't like it if you turn off or this thing on a circuit diagram, or these things if you do electronics. But basically, an inductor is just a slinky connected to electricity, and it doesn't like it if you turn off the electricity running through it. You can think of it like momentum. The electricity has some oomph as it's going through the inductor, so as you open the switch to turn off the power, the current doesn't just stop. It keeps flowing toward the switch, building up charge until you get a huge voltage across the switch, and at some point the voltage will be so high it can jump across air. Or in our case, across the small part of the switch that's still partially touching, so you get a ton of current running through a tiny piece of metal, and it gets really hot really fast. This aspect of induction used to be used in some car ignitions because you'd need a really high voltage. So once you opened a switch connected to an inductor, you got a really high voltage that could turn on the ignition. Induction was also used to create the earrings that I'm wearing, which are shrunken dimes. We used a giant electromagnet to shrink coins. I made a video explaining how that works, so check it out. Why the electricity doesn't like to turn off? That's an interesting question, and I find it really intuitively difficult to understand because it's a result of Faraday's law of induction, which says that if you change the magnetic flux, and I love the idea of flux because it's the amount of something through an area. So in our case, it's the amount of magnetic field through the area of the coil. And we're changing that by turning off the electricity. The electricity is what's creating the magnetic field, and when you turn off the electricity, the magnetic field shrinks, which means the magnetic flux goes down. Now this change in magnetic flux causes an electromotive force, which acts like a voltage. And that pushes back against the change in current that changed the magnetic flux. But what does this all mean? The math is there, but what does it mean? Now, the best way I can find to understand it is that it's kind of like a conservation of energy. When you run current through the inductor, it builds up a magnetic field. And it took energy to create that magnetic field. So the magnetic field is storing energy. When you turn off the current, the energy can't just disappear. It has to go somewhere. Energy conservation, brew. Yeah, that energy doesn't just disappear. So it goes into a flowing current that ends up raising the voltage. I went down the rabbit hole of trying to understand induction intuitively, and I got to special relativity, the way that magnetic fields relate to electric fields, and let me tell you, that's fascinating, but it's beyond the scope of this video. Here's another metaphor. This is all kind of like how a water hammer works. If you've ever turned off a valve in your house really fast, you hear this like boom, this knocking. That's called a water hammer, and it happens because you've got water flowing through the pipe, and as soon as you shut the valve, you're blocking the flow, but it's still going. It's got that actual momentum, and it'll smack into the valve, and you get kind of this sloshing of momentum back and forth. But to me, the interesting stuff is what's actually happening, and that is the fact that inductors have stored energy, and that energy has to go somewhere when you turn off the electricity. Inductors protest. It's not just the #resist stores that protest. I had a lot of fun trying to really understand how to explain it. Hi, this is Diana. You're watching Physics Girl, and this is my dad, Bill. You're an unusual man.
Well, I certainly have an unusual daughter.
I guess that's fair. So do you know what I want to ask you about?
I do.
What is that?
It's about lightning and my experiences with lightning. The first one was when I was probably...
Wait, Dad, wait. What is your experience with lightning?
I was hit
By lightning?
by lightning, yeah.
Twice.
Yes.
Not like bolt to the head.
Not like bolt to the head, no. Close enough that it had a direct impact on me.
Tell me about the first experience. What did it feel like? What was the situation?
I was, I think, about 12 years old, and I was swimming in the lake one afternoon when a thunderstorm came toward us at the other end of the lake, which was probably about 7 miles long. And some lightning hit the water from quite a distance, and we could feel tingling in the water, and we decided at that point we probably ought to get out of the water. And so I was walking up through the pines to go home, and then everything went black. And I woke up probably an hour and a half later.
Wow.
And the tree was still smoking from the bolt that had come down the tree.
So the lightning hit the tree.
Yes.
And some of it probably went through you.
Some of it probably did.
Yeah. So you woke up next to the tree.
Yes.
And that was the moment you decided to become a tree farmer. He really is a tree farmer. Like, it's true.
But it's pretty significant when you're just suddenly standing and suddenly you're not, right? I felt strange when I woke up. I was dizzy and I couldn't remember what happened. I couldn't even remember walking up from the lake.
What did it feel like the second time you were hit by lightning? Because he was hit twice.
I was probably 35 years old. I decided, since it was thunderstorming outside, I would do something in my garage underneath the house. There was a large tree 20 feet from the garage, and the bolt came down the tree.
A tree again.
A tree again. I was bent over, and it caused an involuntary muscular situation where my whole body straightened out, everything went up like that, and I had no control whatsoever of that happening. It was just very similar to what happened to me once when I made the dumb mistake of crossing a 220 with a screwdriver.
You would.
I would, and I did, but the electricity causes this involuntary movement of your muscles, and it's just,
right.
You can't even control it.
First, I want to show you a little experiment we did.
Okay.
So it's an experiment to show how lightning forms. So we made it from like PVC pipe, and you just charge it up by rubbing PVC pipe on this metal sphere, and then...
Whoa.
Did you see that?
Yes.
Does it bring back some memories? Charge it up by rubbing PVC pipe on this metal sphere, and then...
Whoa.
Did you see that?
And I did, but the electricity causes this involuntary movement of your muscles, and it's just,
right.
You can't even control it.
First, I want to show you a little experiment we did.
Okay.
So it's an experiment to show how lightning forms. So we made it from like PVC pipe, and you just charge it up by rubbing PVC pipe on this metal sphere, and then...
Whoa.
Did you see that?
Yes.
Does it bring back some memories?
That's a pretty good arc.
It's a pretty good arc, right? I may have a video next week on how to make this setup. You just stay tuned. But then we wanted to show, what that jolt might do to a person. And so we made a little ham man.
A ham man.
Wait, look closely, because there it was.
He looks okay.
The whole point of doing this shocking demo was to sort of replicate lightning, but also to figure out why lightning is so dangerous. So there are a few key differences between actually getting struck by lightning and shocking Ham Man. For one thing, when you get hit by lightning, it doesn't necessarily drop a bolt right down on your head. In fact, a lightning bolt is only about an inch wide. So to get that spark, we charged up the bowl to about a couple 100,000 volts, which sounds scary and life-threatening, but it's not. And here's the reason why. The difference between voltage and current. I like to think of it like standing under a waterfall. In order for the water to knock you over, you need, one, for the waterfall to be tall, meaning it needs to have a lot of gravitational potential energy to start with, and two, a lot of water flowing. Electric charges are similar. The higher voltage, the more potential energy each charge has, and then the higher current means more charges are flowing. Our metal bowl demo had a really high potential energy, that is a high voltage. But it's kind of hard to get a lot of charges on there using the paper towel method, so it had a low current. I mean, don't get me wrong, it's not fun to get shocked by that thing. It's like getting spit on by someone from the top of the Empire State Building. Being hit by lightning would be like standing under Niagara Falls. It's got volume and height, so that's high current and high voltage. A lightning bolt has tens of thousands of amps of current and millions of volts compared to our couple 100,000. So your heart is especially susceptible to lightning because your heart is a muscle too. What a workout it is to love. So the electricity of the lightning can kill you by messing your heartbeat up so much that it stops working.
A lot of people have described that feeling of their muscles locking up and like not being able to control their muscles anymore.
Zero control, right?
Yeah. And you're lucky because other people have described their mood and their personality changing after lightning strikes.
If you survive a lightning strike, you might also end up getting these eerie pink patterns on your arm that look like branches. They're called Lichtenberg figures, and they're the same patterns that lightning makes when it strikes wood. So in conclusion, it's not a great idea to get hit by lightning. So what should you do if you're in a lightning storm? Some tips for lightning storms.
Don't be next to a tree.
Don't be near a tree. So typically being inside a building or inside a car are very safe. I mean, you may feel the lightning as in your situation, but you have to be really careful not to touch the outside of the car though, because with a Faraday cage, the lightning will travel along the outside. So even if you're inside of a car and you happen to touch maybe some of the metal parts of your car or the outside of the car, well, you can draw it, through your body. Boating is where most lightning deaths occur, like being out on the open water.
So it was good I got out of the water, right?
Good you got out of the water, absolutely. Good job. So to all the surfers, divers are higher, and you can come to the aid of some of the other people.